Hey there everybody, Mr. Mark with you, and today we are discussing floating things. Actually, not just things that float, but all things that get submerged in a fluid. Believe it or not, right now you are submerged in a fluid. You would call that fluid air in all likelihood. And there is somewhat of a floating action when you are submerged in air. Now, it's very, very small for you, but for other things, you could notice it, like for instance, a helium balloon. So here I have water. You can't tell that's an aquarium full of water, and you're looking as close as I can get straight at the edge of the water so you can see above it and below it. And you should see a styrofoam disc that is floating on the water, and a very, very tiny amount of the styrofoam disc is submerged. If you kind of get a little bit more underneath the water, you kind of see there's just a little tiny fraction of that disc that is submerged. And you've probably floated in swimming pools and things like that before, and so you might kind of instinctively know a little of this already. The first thing that you might notice about things that are floating is that when you put more stuff on them, like if you push down with your hand, or if you add a 500 kilogram weight to it, that more of that object goes underneath the water. And so the first kind of thing to learn about the buoyant force, which is the name of the force that the water is exerting pushing up on my raft, is that it depends on the volume of whatever is submerged in it. And if you do a little bit more careful experimentation like we will in just a minute, you'll find that it's actually the weight of the water that is displaced. And so the styrofoam disc, when I take this mass off of there, will pop right back up to the surface. It actually takes a lot of force to get this thing submerged all the way underneath the water. And then when I take away that external force, it pops right back up to the surface. And so one thing we're going to do later is we're actually going to calculate the maximum buoyant force of this styrofoam disc and figure out exactly how much weight we can put on it before it starts to sink. This thing will actually hold up quite a bit. So a 1 kilogram weight, and now it's really getting submerged. The hardest part is keeping it from tipping over like it did right there. So first thing to know is that the buoyant force depends on how much of the object is underneath the surface. The second thing to know is that the buoyant force is there for all things regardless of whether or not they float. So even things that are sinking have a significant, possibly, buoyant force. So I've got 3 spherical objects. See if I can get those in the frame. A wooden ball, and then a ball bearing, and then like a marble like that. And what we're going to do is we're going to drop all 3 of those things in the tank and see if we can determine what happens. The wooden ball is easy. The wooden ball just floats. Observe what happens with the marble and the ball bearing. Those things are about the same diameter, so any drag forces should be appreciably close to being the same. Kind of drop these things back here. 3, 2, 1, go. That was kind of fast. I don't know how to do slow-mo and then return to normal. But you should have noticed that the ball bearing went down faster. So those things would have had about the same buoyant force because they have about the same volume. So the next important thing to know is that weight is still a thing. The buoyant force doesn't take away the weight. It simply, in some cases, balances it or attempts to balance it. So the buoyant force is always going to push upwards, whereas weight is always going to push downwards, just like it did before. So let's do one more quick demonstration. Here I have a spring scale hooked to a 500 gram weight. Lift this thing up so we can see a little bit better. And you'll notice that the spring scale is reading just under 5 newtons, which is what it should, because a 0.5 kilogram weight should weigh about 5 newtons. When I submerge this in the water, notice what happens to that spring scale. It was reading 5 newtons, now it's reading closer to 4 newtons. And so that thing, if it could sink, it would sink. The scale is still holding it up, but it doesn't have to exert as much force as it did before because of that buoyant force. When I pull it out of the water, it goes back to being 5 newtons, just like it was before. And so regardless of what thing I put in the tank, it's always going to have a buoyant force acting on it, and that buoyant force is going to be proportional to the volume. And so over here we got some pictures. Buoyant force, weight of the fluid displaced. And so if I have a tank of water, it initially has a water level, if you will, 0.9 liters. And then I submerge an object in it, and now the volume is 1.1 liter. Then the weight of 0.2 liters of water is equal to the buoyant force. And so doing a little bit of math, remember that weight is simply m times g. For fluids, typically it's easier to do volumes rather than masses. And so if we invoke the old density formula, density is rho equals m over v. We rearrange that to get m by itself, we get rho times v. Now we can write that the weight of that fluid displaced is equal to rho v displaced times g. Now it's important to note that that is the density of the fluid, not the thing that you're putting in there. For things that are floating, of course the net force would still be equal to 0. The more stuff that's in the water, the bigger the buoyant force is. And so that's why more weight means more of your object submerged. So the forces would still be balanced. Right underneath there, there's a picture of something that's sinking, where the buoyant force just isn't big enough to overcome the weight of the object, and so the thing sinks. And then you could even do the reverse, like for the raft I pushed under the water, have a bigger buoyant force than you do the weight force. So let's go back to this idea of how we got to the rho vg equation for the buoyant force. So we're going to do a little bit more careful experiment. Over here I've got an empty beaker, and don't worry about the fact that it's got a little bit of water in it, because on this balance I'm going to push the tare button, so now my beaker weighs 0. I'm going to bring this beaker over here. I'm going to put it underneath the spout on this bigger beaker, which is full almost completely to the top with water. And what we're going to do is we're going to submerge something in there and catch the liquid that is displaced, catch the volume that is displaced. So I'm going to use the 500 gram mass again for that. So I've got that on my spring scale. And again, it weighs about 5 newtons. I'm going to look at the gram side. So it's about 480 grams or so. And so I'm going to submerge this into this beaker. I'm going to catch the water. That worked earlier, practice a little bit better. So a little bit of water spilled, but I still got most of it in that beaker. Now notice that it's saying a mass of like 430 or so. And so what's missing from 430 to 480 is more or less like 50 grams of water. Now, some of my water ended up on the table. Let's go see if we got somewhere in the ballpark of 50 grams of water in my beaker. All right, I guess I spilled a little bit more than I thought I was going to spill that time. If I have time, I'll repeat that little bit of experiment with some better equipment. But the water that was displaced, so that would be the water in that beaker and the water on my table, which, something in the neighborhood of 50 grams, is equal to the force that was exerted upwards and what caused that spring scale to go from 5 newtons up closer to 4. And so if you do that with some more careful equipment, you can prove that the missing force is equal to the weight of the water that's spilled out of there. And again, if I can get some better equipment, well, maybe I'll repeat that shortly. So that's kind of the big idea. That's often referred to as Archimedes' principle, because Archimedes first recognized that when he was trying to show the density, so there's that density term again, of a crown was equal to that of pure gold. But that's a history story, so I'll save that for a separate video. So as you go through the video lesson today, you're going to be learning a few more details, do a little bit more rigorous proof of why the buoyant force is equal to rho vg, why it always points upwards, and then do a little bit of practice with things both that are floating and things that are sinking. Until next time, ta-ta.